Happy Wednesday, and thank you for joining us for Tech Talk today. I'm going to pass things over here to Dave Cleland to talk to us about RF basics and something Shannon told him once.
Exactly. Something Shannon told me once. So we have there's always questions when around the wireless business, whether you're the technician that's fixing it, you're the planner that's installing it, or that's planning for it, or you're the installer that's making it work, whatever the case. I need to know if I'm getting the performance from my wireless gear that I should. The manufacturer's data sheet often says one thing, but I'm seeing much different performance. And why is that? So we're going to, over this next 45 minutes or so, we're going to talk about how to know whether or not you're getting the performance that you should be over any particular wireless system. Now, in Tech Talk here, we try to be brand agnostic. And so this is definitely one of those situations where it does not matter about the brand, because we're going to talk about the physics of getting data from one place to another. All right. How do I interpret a data sheet? Often it contains phrases like up to, often lists the maximum, right? So if a system can go 75 miles and it can do 75 megabits, then the spec sheet says it goes 75 miles and 75 megabits. It's up to you to interpret that to mean, well, 75 miles at 1 megabit or 75 miles at 75 megabits, or what's the real conditions here. And then sometimes it'll say, oh, it's good for 600 megabits, but they don't tell you in the spec sheet that you need the license to go from 100 megabits up to 600 megabits or something like that. So they can be really confusing. And so once I get a system in place, I need to know how it's working. So let's eliminate some of the fog today. Let's go over a simple little bit of physics that we're going to take and use to answer lots of questions that I'm sure some of you have. There are some very well understood laws of physics that describe the volume of data that can be transmitted through a channel. In college, we learned about these things. Most of us promptly forgot it. As soon as we were done the exam, we walked out the door and it became a blur. So some years ago, while I was noodling over a particular problem that an operator had, some of these principles came back to mind. And we felt like old Newton sitting underneath the tree there, and down falls the apple. And oh my gosh, this is the answer. So let me introduce you to Shannon's equation. This is what Shannon told me once. He said that the capacity of a channel is related to the bandwidth of the channel and the signal to noise ratio in the channel. So we have signal power over noise power. And so the equation is actually quite simple. The bandwidth times the log to the base 2 of 1 plus the signal to noise ratio gives us the upper capacity of the link, given the situation right here that is variable is the signal to noise ratio. So as we go farther, of course, the signal signal to noise ratio decreases, the noise floor stays the same. As we're closer in, the signal level increases, the noise floor again stays the same on a uninterfered with channel. And we can calculate then what our bandwidth in that channel is supposed to be. Let me give you some examples here. Let's calculate some examples. So I'm going to use a bunch of examples over the next couple of slides here. We're going to talk about what the values I would expect out of a particular channel are. So let's say, for example, we're going to talk about TV white space. Now, these TV channels are 6 megahertz channels. The latest equipment from Radwin can bond up to 4 of these together, but let's say I've only got one. Let's say that as I am looking for TV white space, I have one channel and I've got a CPE out there, and it is experiencing 20 decibels of signal to noise ratio right here. So when I apply my calculation to this, I've kind of skipped the math in here. You just have to trust me that my calculation is correct. On this 6 megahertz channel, I can expect at 20 dB SNR, I can expect to have 26 megabits as my maximum capacity in the channel. The units are always, in Shannon's equations, we're talking about bits and we're talking about hertz, and we can correct the formula because it's a logarithm, we can correct it for megabits and megahertz. And so we end up with a 6 megahertz wide channel. We can calculate the number of megabits that we can support in that 6 megahertz channel. Let's look at some other examples here. All right. So here's my 6 megahertz channel at 10 dB signal to noise ratio. Well, it's down to 21 megabits. Remember, the signal to noise ratio is one of the factors of my channel. So my 6 megahertz channel, if my signal to noise ratio is down to 10 dB, I got 21 megabits per second possible in that channel. If I'm using an LTE system, perhaps at 20 megabits, and again, my target SNR is 20 dB signal to noise ratio, then I can expect 88 megabits in that channel. Again, this is just purely by the calculation. As I increase my channel width, look at what happens here. The bandwidth goes up. On a 40 megahertz channel at 20 dB SNR, I use the same SNR on these three to just show what the difference is. I'm up to 176 megabits in that channel. At 80 megabits, now we're talking about EP&P and maybe Mimosa and maybe some others. If I have 20 dB SNR in the channel, then I have 351 megabits that are possible within that channel. Well, that's really good to know. So this is even more interesting. When I plot I vary my signal to noise ratio over a particular channel width, what I find are some very interesting things. At 6 dB signal to noise ratio, I have half my capacity. At 12 dB signal to noise ratio, I have 3/4 of my capacity. So there's 10, there's, whoops, yeah, 5, 10, 15, 20, right here. I've been staring at the screen all day here, so forgive me, I can, so right about there, I have about half my channel capacity, 3/4 of my channel capacity. I have half there. And at 24 dB signal to noise ratio, right up here, I have 90% of my channel capacity. So as I increase my signal to noise ratio even more, my capacity does not increase a significant amount. And by this equation, I actually never get to 100% of my channel capacity, because that would mean that the signal to noise ratio would have to be infinite for me to hit 100%. This is how the world behaves. Oh, come on. There we go. I always get bothered by the phone when you just don't expect it. But anyways, so again, 6 dB, I got half capacity. At 12 dB signal to noise ratio, I have about 3/4 of my channel capacity. And at 24 dB, I have about 90% of my channel capacity. These numbers are kind of important, because as we plan our network, as we have to make a decision at some point what our minimum installation threshold is going to be if we're going to base our network on capacity. These days, networks are almost never based on coverage. So I do not want to connect CPE that are down here in the sub 5. I don't want CPE here. Maybe I don't even want CPE here, because this is going to be too much of a load on my network. Maybe If I'm actually going for a high service level, maybe I don't even want to connect CPE that are in this range. Maybe I don't want to connect those in there, and maybe this is what I want for my connectable CPE. I want to have maybe 18 or 19 or 20 dB signal to noise ratio as a maximum, maybe, and in order to get the most out of my channel that I possibly can. This is the reason why, if you've ever been on any of my courses, that I often talk about an installation floor, a threshold that you don't want to install below, because it's going to take too much time to deliver the service to that subscriber that has the low signal to noise ratio, and it's going to take away time and capacity from all of my better quality subscribers that are on the network. This is the root of that theory, is Shannon's theorem. Now, all right. So the capacity, the thing to remember here is this statement right here. The channel capacity is directly relational to the channel bandwidth. It's the channel bandwidth is the primary driver for how much capacity we have. Then, secondary to that, the signal to noise ratio modifies our channel capacity. And of course, when we have signal equal to noise, we have no capacity in the channel. When we have signal infinitely higher than the noise, at 30 or more dB, we have all of the capacity that our equipment is capable of. Okay, so far, all this is theoretical. Got to break this down and bring it into focus for a real channel, some real equipment, some real, some comparisons to what we would really deploy out in the field. So all of our systems, multi-point systems that we deal with, are time division duplex. The licensed microwave systems that we deal with are frequency division duplex, meaning that the transmit and receive is on at the same time. But our multi-point systems are time division duplex. Our point-to-point systems in the 5 gigahertz band are time division duplex. We dedicate some time to downlink. We dedicate some time to uplink. And so we have this TDD ratio that we have to modify. So that those numbers that we've seen so far, that was if I had 100% of my time available for transmission in one direction. Then I could get that 88 or whatever the megabit, whatever the size is, 176, whatever it happens to be. But that's not the case. I'm going to take some time for downlink, and I'm going to take some time for uplink. Maybe it's 75% time downlink and 25 uplink. Maybe it's 50-50. Maybe it's 90-10. Who knows? Whatever it is. And then I'm going to have, these days, there is almost no equipment out there that doesn't use some form of MIMO. So two-stream MIMO is the workhorse of broadband wireless today. So in almost every type of network that we have a two-stream system. When the signal to noise ratio is poor, the two streams contain the same data, so that it increases the power density at the receiver and decreases the effective, or increases the effective signal to noise ratio, so that we can pass a little bit more traffic at that low signal level. As we cross some sort of threshold someplace, we go to two-stream MIMO, where we're going to put different data on each of the streams, so we double our capacity. We need to know, what we really want to know is, we want to know what the capacity of this MIMO channel is. Now, what about multi-user MIMO? This is another new thing that has come along in the last few years, where I'm able to talk simultaneously to a number of subscribers in different groups. So how many groups do I have? What is the effect of that on my available bandwidth? Now, one other thing is that every broadband wireless system today uses some sort of forward error correction and some sort of retransmission algorithm. So how do we account for this? We'll see that. And then when you put all this together in software, there's always some kind of implementation loss. Always there is there's something less than 100% efficiency in bringing all of these algorithms together. We need to, for example, wait for propagation to end when we switch from downlink to uplink. For example, we can be sending data, then we have to stop sending data in the downlink. We have to wait for the data to get to the farthest CPE because it's only traveling at the speed of light. So it does take some number of microseconds to get from here to there. And so I consider this all to be implementation loss. We need some kind of factor to consider to actually deploy all of these in real life. So got our four factors to bring this to real world. So it happens to be that my favorite proverb is Proverbs 25:2. It says, "The glory of God, it's the glory of God to conceal a matter. To search out is the glory of kings." So a modern revision of this: consumers in the internet demand more capacity. So it is the glory of the consumers to use all the data that they can, and it is the glory of the manufacturers and operators to search out how to deliver without breaking the bank. So this is where we're coming from here. We need to know what we can deliver so that we avoid, even more so today, we avoid the issue of oversubscribing our base stations and over-promising services, and we need to know what that number actually is. This is the way to do it. So let me take an example of some fictitious broadband wireless equipment, and I've put some transmission protocol numbers, values here in our system. So 20 megahertz for channel bandwidth. Probably 75% of all broadband wireless equipment running out in the field today is running on a 20 megahertz channel. Probably 90% of it is running in MIMO of some sort. So there's two stream MIMO, so we count two streams. In our downlink time division duplex ratio, we're going to count that 0.75% of the time we're spent in downlink and 0.25% of the time we're spent in uplink. We're only going to count the downlink here in this, in our calculation here today. Our air protocol efficiency, we're going to set our implementation loss at about 80%. That should take into account the switches between downlink and uplink, and the fact that we might have a beacon, the fact that we might have a preamble, or we might have pilots, or whatever the case is that we have to account for that time. We don't have all of the available channel for customer data. So there's some overhead. So let's count 80% for that overhead. And then forward error correction. I think one day I'm going to have to do a tech talk on this, because forward error correction is quite misunderstood as to what that actually means. We all see modulation levels like for example 64 QAM 2/3. So what does this mean? 64 QAM, for example, means that I've got 6 bits per symbol that I'm accounting for. So I have 64 different states so I can count for my 6 bits. And the 2/3 at the end is the forward error correction. What this really means is that for every 6 bits, if you see, so for every 6 bits, I'm going to use 2 bits for forward error correction, for error correction. I'll call it EC here for this. So if I'm at 64 QAM 2/3, I'm using 2 out of my 6 bits for error correction. I'm using 4 of my 6 bits for subscriber data. If my forward error correction were 3/4, for example, now I'm going to use 3/4. Yeah, 3/4, 5/6. Let's go 5/6. 64 QAM 3/4 is not very, very convenient. So 5/6. So at this rate, I'm using one out of my 6 bits let me write that better. My 6 bits, I'm using 1 bit for forward error correction, right? I'm using five of my bits for subscriber data, and I'm using 1 bit for error correction. So I've got to take that into account. So my forward error correction here, I'm going to assume that there's an average of 3/4 across all of my modulation levels that I have. So I can be as high as 5/6. I can be as low as 1/2. QPSK 1/2 is oftentimes the lowest. So that means 1 bit for the customer, 1 bit for error correction in that situation. So when I multiply my overheads together, I come up with a utilization ratio of in this case 0.45. When I multiply 0.75 by 0.8 times 0.75, I come up with 0.45. In my calculations that are coming up, you're going to see a few slides here that are going to show the calculations. I am going to make the assumption I'm going to serve a 50 megabit service. And I'm going to assume that I can achieve a 10-to-1 oversubscription ratio. So let's see what this all looks like. All right, so from our example network here, I have my SNRs, them capable up to about 33 dB. I've plotted the capacity from Shannon's theorem and multiplied by my efficiencies that I have that I've assumed, I've made assumptions for. I come up with a number of values. So my capacity, using this system that does two-stream MIMO and all of its other characteristics here, at 6 dB, there I have 51 megabits of capacity. At 12 dB, I have 67 megabits of capacity. You see where this is going, right? At 24 dB, right here, I have about 84 megabits of capacity. So this is a little bit less than the theoretical because of the fact that I've got my overheads. My overheads aren't changing. As I increase my signal to noise ratio, I'm not shortening up my time values for my overheads. So my overheads are staying the same. So here's what I have. Here's what the plot looks like. If I had a weighted average performance across my sector of 15 dB signal noise ratio, I would expect, if I can draw another straight line here, I would expect about 70 megabits of downlink capacity on that system. And if my performance, my network management system every night said that I was hitting 70 megabits, the system is probably running perfectly for the conditions that you're asking it to run in. If I increase that signal to noise, that average signal to noise ratio, so in other words, I'm not going to connect some of the lower signal to noise ratio customers to this sector. I'm going to take and build another site or connect them some other way so that their signal to noise ratio is higher. If I was at 20 or 20, say 22 or something like that, dB SNR, somewhere up there, then you can see that we're at the 80 bit megabit line on this particular network. Then when I take my service level, I want to supply a 50 megabit service and divide it by or multiply it by my 10-to-1 oversubscription ratio. I now end up at this 22. If 22 were indeed my average, I could support 16 or so CPE on that sector. Something like that. If I had this sector in these conditions and I had 30 CPE on it and I'm trying to serve this 50 megabits to it, I would end up with a flat line on my performance. My throughput graph would end up coming up to this 80 or so megabits and it would flatline. And my availability then goes way down because I can't introduce new conversations onto my network. My customers start to get unhappy. Even though I'm passing all the traffic that this sector was designed to, my customers are not pleased with me and they're, threatening to go to Starlink, whatever. It seems to be the rage lately as I'm watching the Starlink group on Facebook and others, is that they're upset with some of the incumbents that we have here in Canada, and so this might be one of the reasons why. Anyways, so I know the parameters that I need to stay. I need to stay in, and so let's take and look at a few examples of actual systems here. Okay, so let's take a 450i for example. We're gonna use a 40 megahertz channel, and it's two group MIMO, of course, and we're going to use some of the same efficiency numbers, and so we end up at the same relative efficiency, our 50 megabits and 10 to 1. Well, now instead of that, if we were shooting for, let's use an easy target of 20 megabits right here for our signal to noise ratio, then we're going to have 160 megabits or so of capacity on the system, and working that 160 megabits into here, I can support 30 plus, between 30 and 35 CPE on that sector. So I hit those numbers, and we call it good. All right. Let's look at another example. Oh, come on. There we go. There's a 450M. All right. So now we've got MU MIMO that's come into this. And so we've got these MU MIMO groups. So we've got two streams, and we've got these MU MIMO groups. So I'm going to make the assumption that I've got 4 groups that my CPE are grouped into. So therefore, I have 8 MIMO streams in this system. And again, I'll use the same efficiencies because those are kind of standard stuff. And at the 50 megabit service. All right. So now at 20 dB SNR, I am just slightly north of 600 megabits possible on this system. And at that 600 megabits possible on that system operating in this, I can support about 120 or a little bit more CPE. All right, so there's my CPE value, and there's my my approximate value of the data that I can put over the air over that. So MU MIMO it makes a huge difference in the efficiency of what I can get out of the sector. It drives my spectral efficiency up. And of course, I can support the higher level services, and making sure that I've got the right queuing, the right QoS mechanisms in place. I can hit that 10 to 1 over subscription ratio, and so that's the kind of performance that I could expect out of that sector. Now, one thing that you've noticed through all of this so far is that frequency doesn't matter, and the range doesn't really matter, because the range, we're taking the range up here in the signal to noise ratio. So if we make the assumption that the thermal noise floor is our only noise, then of course the signal to noise ratio is directly related to the signal strength. If there is some interference, as often is the case in 5 gigahertz, we may not have the thermal noise floor as our minimum noise. We might have extra noise caused by the interference of nearby base stations and other people that are using the spectrum. So we might be, if we had 6 dB of noise, for example, remembering back to our link budget discussion, that would mean that we actually have half the range in order to achieve that same signal to noise ratio, because our noise is 6 dB higher than so we have to increase our signal strength by 6 dB. How do we do that? We take and shorten the range up by half. So if in this situation with just thermal noise as our interference value, we would be, let's say, I don't know, maybe 10 kilometers or something like that, or maybe 8 kilometers. And if I had 6 dB of noise in this, I would cut my range in half. So then my maximum range to achieve this kind of performance would be 4 kilometers. So in all of this, we're getting through this simple little exercise here, we're going to have a really clear view of how our system is performing. From a planning perspective, we're going to be able to take and know for sure how many sites that I need. There's no point in putting up a site and seeing what it'll cover. That's those days are long gone. We cannot be deterministic enough in our service provision to be able to do that. So if I need to limit my range to 4 kilometers because of the noise floor or whatever it happens to be, fine. Then those are the conditions that I know I have to work within. And of course, the push has to be for ISET or Industry Canada or the FCC in the US to make more spectrum available so that we can make use of these wider channels. Wi-Fi 6 is a great example of that. Wi-Fi 6's gains, even though Wi-Fi performance hasn't changed a bit as we're going along, but the addition of OFDM, so we have group scheduling, we have multi-user MIMO, we have two-stream MIMO, and if we use 160 megahertz channel indoors, then we get this multi-gig performance out of that kind of equipment. In the outdoors, of course, we have interference and other things that we have to deal with. We don't have the same plethora of spectrum, and we are limited by how much power we can transmit. So we have to live with the world as our FCC and Industry Canada and whatever the government agency is around that is regulating what we see and what we can do. LTE with MU-MIMO. Let's look at the numbers for that just for a second, because this is where all of the LTE systems are going. I mean, as 5G comes along, MU-MIMO is going to be the first part of that. The second part is going to be that we increase the channel width, and by doing that, we increase the spectral efficiency. And so this is kind of the pointing towards the future. So if I take 2 streams of MU-MIMO in 2 groups, if I break the sector up into 2 groups only, on a 20 megahertz channel at my same 20 dB signal to noise ratio, if that's my average, now I'm talking about 140 or 140 plus megabits or so on the sector. And then in my 50 megabit service, right here, I'm talking about 30 CPE per sector. So that's in a rural environment, that's probably not bad. That's okay. If I take LTE with carrier aggregation, which is our way of increasing our spectrum, and if we use carrier aggregation and there's only one group, for example, the difference between the 40 megahertz spectrum and the 20 megahertz spectrum. Now I'm actually with only one MU-MIMO group, I'm actually at a higher throughput. I'm at 160 than I was before, and so I'm serving more than 30 customers at that rate. If MU-MIMO is operating and I have 2 groups, well then of course I'm pushing this even higher, about 45% higher, and I'm serving about 50% or 45% more customers. And 4 groups, 4 MU-MIMO groups seems to be the limit of antenna technology today that we can support. So maybe 4, maybe 5 groups, something like that, and we'll see. You can see that the improvements are huge. And so as we're planning new networks or as we're replacing old networks, these are some of the things that we have to think about is how we are going to achieve some of the spectral efficiency that we need to be able to deliver the services that our customers want. Now, one last example here. We've all heard of Terragraph. Cambium have a product, Radwin have a product, Ciclu have a product. Lots of people have products of Facebook's Terragraph. So I just did a quick little run on what I see for the numbers for Terragraph. Remember, it's a mesh, right? It uses a single single stream protocol over the air. It's 50-50. My implementation loss is a little bit higher because of the fact that I'm doing a mesh. My forward error correction is the same, but my total overhead, my efficiency is about 20-25%, give or take. If I want to supply an 800 megabit service at a 5-to-1 oversubscription ratio, I end up at pretty much the same value that you know, I'm at 12 or so CPU, 12, 13, 14 CPE per sector. And you can see our rate curve here is that if we're at 20, we're just over 2 gig in our capacity. And in fact, Terragraph touts that 1.7 gig in each direction is so right about here. So we're expecting that the SNR, the actual average SNR is going to be somewhere around 10 or 14 or 15 megabits, something like, or 15 dB, I should say, not megabits, dB. Let me make that line straighter. And that's the performance that we're going to expect out of that particular network. If I bond two channels together, of course, I'm going to double that. So, but the channel bandwidth you see up in 60 gig, 2.1 gig channel bandwidth in that particular case, and we're only using up to QAM16 in modulation level in order to achieve our values here. So what I haven't talked about, if you haven't noticed, I have not talked about the actual modulation level. I have not talked about you know, some of the other characteristics that we see on the spec sheet, because I wanted to be able to enable you to go beyond the spec sheet and approach the physics of what's going on, to be able to verify that what the spec sheet says, number one, is attainable, and what the conditions are to attain it, and number two, what my actual network, once I get it deployed, once my network is what it's actually doing out there. If I expected, let me back up here a minute. If I expected particular performance out of a network, and I was only achieving, you know, something much less than that, let's say on a MU-MIMO network, I'm only getting 80 megabits or something like that, then what that's telling me is that my effective signal to noise ratio is like 4 dB or something in that range, and I have a problem somewhere. So do I have a planning problem? Do I have an implementation problem? Do I have an RF problem, or do I have an equipment problem? Those are the places that I need to look. But at least I know that something isn't right, and I can spend some time and effort to be able to identify what that problem really is. All right. So this process can work for point-to-points also. All we need to know is same parameters, right? We need to know that it's FDD, and we set the TDD efficiency to 1, because now we're transmitting continuously in both directions. But otherwise, there's forward error correction. There may not be you know, there's no turnaround or anything like that. So our efficiency is going to be 100%. But I can use these values of this worksheet to be able to estimate what I'm going to get out of a particular point-to-point. And of course, as I was writing the worksheet, I did a couple of links in Link Planner and came up with the values. And yes, they're very, very close. Very, very good. So the physics works. When I'm analyzing the performance of my network that I already have in place, I want to take and make sure that I understand what the effect of the various parameters that I've got. What is my efficiency of retransmissions? What is my you know, and just be able to calculate that out. So there's a lot of troubleshooting that we can do from a system point of view on the network with a pencil, or a spreadsheet, I should say, rather than having to, you know, go out and do testing and drive test and do throughput at customers or whatever the case happens to be. If we're not getting the performance that we expect, then you're never out of ideas to be able to take and test, because this will take and going through an exercise like this, like applying Shannon's theorem, we can take and see if our RF is okay. One of my primary tenets in troubleshooting is always to divide the problem up so that you know what's good and you know what's broken. And then if we can decide what's good and what's broken, then we can take and concentrate on what's broken, of course, and we can fix it. If we don't know what's good or what's bad, and we're just troubleshooting with a shotgun, well, you're going to start replacing stuff. And when you're finished replacing everything, the state of the system is going to be exactly as it was before, and you won't have, really learned anything except how to replace equipment. So when I'm analyzing my network, make sure the parameters are correct. Understand what your network is doing. Read your current system peak performance as a function of this signal to noise ratio. When we start to think of the world in terms of SNR rather than in terms of bits and bytes and dB, MRSSI or RSRP values in LTE, whatever it happens to be, we think in terms of SNR, then we get a much clearer picture as to what's going on. As long as you have no blocking in the backhaul, your net sector busy hour throughput should be a function of the weighted average signal to noise ratio. I could have went through the process here. I might have a little bit of time, but I didn't plan on the process of calculating a weighted average. Most people are familiar with averages, but a weighted average is a little bit different. And so the weighted average, ping me offline, send a note to marketing at mbsiwave.com, and I can go through a little how to calculate weighted average. We can figure out what the actual performance value of your sector should be by the theory, and then you compare it to what it is, and that's really good information. And then use that value to predict the number of CPE that can be supported on that sector. So again, if the oversubscription ratio that we're achieving is 5-to-1 or 6-to-1, you need to be able to calculate that. So you need to be able to know how much traffic is transpiring over your network at busy hour, and you need to know what the real demand is on the network, so that you can compare that and you can figure out what this oversubscription ratio is. That may be another exercise that we need to do, is a detailed oversubscription ratio lesson, but we'll get to that one day also. And then with the service level required parameter, then substitute the actual demand to get the minimum and maximum number of supported, or minimum or maximum, that should be an or, maximum number of supported CPE. So when I know this one, then I can easily calculate this one, and I can easily tell if my network is being oversubscribed. Now, in some cases, networks like some of our ubiquity operators out there, they know that they can only get 5 or 6 or 10 CPE or 20 CPE on a sector, and the performance starts to fall apart. And it's the same with any system. Actually, there is some point where we get to what I call the performance knee. My performance increases to a point, and then all of a sudden it does not increase anymore, and latency goes up, and all sorts of other things end up in trouble. So we need to take and be able to relate all of those issues back to this business of signal to noise ratio. I think I said a mouthful. So any comments that you have, any suggestions that you have for new topics, any comments on this particular Tech Talk or on any of the ones that we've had so far, please send a note to marketing@mbsiwave.com, and Nicole and I will take and go over them, and we'll answer questions. We'll answer whatever issues that you bring up in your emails. If you want a copy of this spreadsheet, it's a pretty simple spreadsheet, and I built it that way on purpose so that it would be really vendor agnostic. Just send a note to marketing, and we can send you a copy of that worksheet so that you can play with your own numbers and you can see what's going on. And last but not least, don't sweat it, and have some fun at learning how the physics of your wireless network behaves. Because once you have taken and put the equipment, you created the environment where your equipment runs best, then everybody is the happiest. You have the least number of breakdowns. You have the system just runs better. And so understanding what those conditions are that you need to create for your particular wireless network is the battle here, and have fun in doing it. And if you have any questions about any kind of system parameter, performance, whatever the case, then feel free to send us a note, ask us a question, and who knows, that could be the topic of the next Tech Talk.
Amazing. Thank you, Dave. So I want to make sure that everybody knows on April 15th, we are doing a special edition Tech Talk, and that'll be our next session. That is going to be on a Thursday instead of the every third Wednesday of the month. There will be a Tech Talk the following week as well, which is going to be April 21st. So Dave, would you like to tell the folks what one they can expect on that special edition Tech Talk, as well as your regular session on the 21st?
Absolutely. So on the special edition of Tech Talk, we are going to delve into, Ryan and I, and we have a special guest, Matt Spruill, are going to take and delve into this whole business of the new licensing fees from ISED here in Canada, and what it means, and what your options are as far as converting some of these links that you've got running in unlicensed 5 gigahertz, maybe moving them up to a license band and getting some real performance out of them, and taking one of the hobbles off of your network by freeing up the backhaul finally at a price that's not going to break the bank. That's the big thing. So that's what we're doing with the special edition of Tech Talk. And the next Tech Talk after that, I will have another special guest. Jeremy Austin is going to be my guest, and we are going to expand on our conversation about quality of service and how to achieve and maintain QoS on your network so that you have as happy a customer as what you can possibly have on your network with the spectrum that you're able to operate in. So that's coming up in April.
Amazing. And if anybody is interested in those links, please hit us up at marketing@mbsiwave.com, and we will be happy to share those sign-up links. Thank you for everything, Dave. This was an awesome session. And like Dave said, if you want that worksheet, please hit us up and we'll be happy to send it over.
All right. Thanks, everybody. Have a great day.
Bye, Dave.